don't know.
Okay, we are happy to have the Jie-qiang Wu from MIT. He's going to tell us about, I don't know how to pronounce it, Peierls bracket and the gravitational grazing in JP.
Oh, sorry, it's a typo. So first, thanks for inviting me. This time I will talk about the Peierls bracket and gravitational dressing in Jackiw-Teitelboim gravity. In this work, we revisit the Peierls bracket, which is a linear response interpretation of bracket computation in covariant phase-space formalism. With Peierls bracket, we studied the commutator between a gravitational dressing operator with the ADM energy operator in Jackiw-Teitelboim gravity. In the talk, I will first give a brief introduction, and then I will give a brief review for the Peierls bracket. And with this Peierls bracket, I will study the Hamiltonian flow of the operators in gravity. I will consider two operators. The first is the area operator, and the second is a gravitational dressing operator. How to deal with diffeomorphism symmetries is a complicated problem in gravity. In low energy limit, it is generally believed that gravity can be described by an effective field theory with diffeomorphism symmetries. And here the diffeomorphism symmetries should be treated as gauge symmetries. And as we know that for series with gauge symmetries, only gauge invariant observables are interesting. For example, the scattering amplitude or the correlation functions of gauge invariant operators. And indeed that the scattering amplitude capture a lot of things, but it is not enough. For example, for this example, this is the two-stat eternal wormhole. And by scattering amplitude, we are not able to study the physics inside this circle. The reason is that the outgoing particle will never go out of the event horizon. So by scattering amplitude, we will never detect physics around here. And then you can see that to understand the physics behind the event horizon, we need to study the operators supported deep into there. And one well-understood example with gauge symmetries is the QED. It is a well-understood example with gauge symmetries. And the gauge invariant operators in this model, including these local operators like this, and non-local operators like the Wilson loop or Wilson line attached on two matter fields, or a Wilson line attached on a matter field and the spatial boundary. And in this picture, I illustrate these operators like this. Say like this is this operator. This is the Wilson line operator attached on two matter fields, and this one is the Wilson line attached on a matter field and the spatial boundary. And from these two examples, from this one and this one, we see that the charged matter fields are always associated with gauge fields. Or in another way to say is that if we create charged particles, it should always be associated with gauge fields to satisfy the constraint equations. And in gravity, it is similar. Because of the diffeomorphism symmetries, the matter fields are also associated with gravitational fields, which is usually referred as gravitational dressing. And the standard treatment for gravitational dressing is to use relational construction. That means when we define operators, say like we define some matter, if we have some matter fields, instead of locating the matter fields by some value in a coordinate, we can locate the matter fields in a covariant way. And by definition, this operator will be diffeomorphism invariant. For example, we consider such an example. We shoot geodesic from the spatial boundary with some given distance, and we measure the matter fields at the endpoint of this geodesic, like in this picture. And actually, this already gave us a define diffeomorphism invariant operators. And maybe here I need to emphasize that here any gauge invariant functional of configuration can be interpreted as a gauge invariant operator. And by gauge invariant functional of configuration, we mean such a following thing. Say like assuming we have an algorithm, this gauge invariant or the function of configuration means such a following thing. Say like we have an algorithm given any class of gauge equivalent configurations, it will read out a unique number. Then this algorithm define gauge invariant operators. And based on this interpretation, we see that with this two step, we indeed define a diffeomorphism invariant operators. And another thing we need to emphasize that even though here we write this operator in such a simple form, but it is a non-local operator which support on the geodesic. And the commutator between this operator with other operator will be very complicated. And it is the goal of this talk to study the effect of these operators. And let me give two motivations to study this gravitational dressing operator. The first motivation comes from the firewall argument. The Marolf-Polchinski firewall argument. The argument, any question? Okay. The argument is the following. Creating a particle behind the event horizon will decrease the ADM energy, which is contradictory to the lower bound effect of the spectrum. So that means that close to the event horizon, the effective field theory must break down. And in this argument, the gravitational dressing is both necessary and complicated. On the one hand, the gravitational dressing is important, as we know that the ADM energy operator, it is some operator which support at the spatial boundary. To have a non-zero commutator, this gravitational dressing operator, to have a non-zero commutator between this gravitational dressing operator and the ADM energy operator, we need this gravitational dressing operator support at the spatial boundary. And then you see that this gravitational dressing effect will play a role here, such that its commutator with ADM energy is non-zero. And on the other hand, it is also complicated because of the nonlinear effect of the gravity theory. This gravitational dressing will have a lot of higher order terms with respect to the gravitational coupling constant. And potentially these higher order terms may change the effect of this operator. So it will be necessary. It is necessary to study this higher order effect with respect to the gravitational coupling constant. And another motivation comes from the Berkeley construction. In this paper, the authors suggest that for the operators inside the entanglement wedge, this is by the way, this is the ADS-FT correspondence. The operators, the operators in the entanglement wedge can be reconstructed by the operator in field theory in a sub-region. But to discuss the reconstruction of the gravity by field theory, it will also be helpful if we first fully understand the operator in gravity. So these two are the motivation. And in this work, we studied the gravitational dressing operator in classical limit, where the system can be described by a phase space, and the operator's commutator will reduce to bracket. And in the following, we will study the Hamiltonian flow of the gravitational dressing operator, from which we can directly read out the brackets between the gravitational dressing operator with any other operators, for example, the ADM energy operator. And then the Peierls bracket gives a convenient way to study the Hamiltonian flow in the covariant phase space formalism. So far, any question?
Are you going to talk about some examples of the gravitational dressing operators? Because in gauge series, the charged matter fields are dressed with the gauge fields by some Wilson line operators, right?
Yeah, yes.
And in the gravity side, so there should be some explicit examples about such kind of dressing.
Yes. But I
Okay.
think here I already gave one example. But
Yeah,
maybe for you you do not feel that you do not think this is an example because I didn't write it by operator. Is this the question?
Right, because this is just a geodesic, right? It does not look like something like Wilson line.
Yes. So here I need to emphasize again. What do I mean that I define an operator? Here I define an operator as a functional of configuration, and maybe gauge invariant functional of configuration. So what do I mean by a functional of configuration? Here that means, for example, consider some simple examples, say like in point particle. Then in point particle example, then X is an operator, P is an operator. Maybe X multiplied by P is an operator. So more generally, if I give you an algorithm such that given any configuration, we can read out a number, then this is already then this algorithm already define an operator, at least in classical limit. But maybe the question, so here the question is, here the difficult part is not to define this operator. The difficult part is that assuming we already define an operator like this, what is this effect? What's the effect of this operator? What's the commutator between this operator with any other operator? And in the very end, we will show how to study the commutator between this operator with other operator. So we will not write it as something like the Wilson line. We explicitly write it as some gauge field or something, some matrix, and we will define it in this abstract way. And but we will show the effect of this operator.
Okay.
Maybe when we discuss the gravitational dressing operator, you will see.
Excuse me, Jie-qiang.
Yes.
May I also ask a question regarding your picture about how do you define the operator using this functional?
Yes.
You said it's a non-local operator, but from the way you define it, it looks like local because you only constrain the boundary condition at that point. Is that right?
I think actually here I didn't precisely say what do I mean by a local operator or what do I mean by a non-local operator.
Yeah.
So actually this quantity, as I said, it is a functional of the configuration. Yes. And to say it is, to say it is local operator or non-local operator, we mean the following thing. We can take a variation for this operator with respect to the configuration, say assuming our theory is defined by some fundamental fields, like the gauge fields, the metric, or some scalar fields. And the variation of this can be written as an integral of the variation of the fundamental fields. And if this integral only support at one point, I will call it a local operator. If this integral support on a surface, then I call it a non-local operator. And in the end, I will show that based on this in this setup, this operator will behave like a non-local operator.
Okay, I see. Thank you.
Okay, so in the following, I will first introduce the Peierls bracket. And the Peierls bracket is a linear response-like computation of gauge invariant operators bracket in covariant phase-space formalism. Maybe we are not very familiar with the Peierls bracket, but actually this Peierls bracket, this linear response thing, we understand it very well in quantum mechanics. So we first start from an example of quantum mechanics. As we all know that in quantum mechanics, the linear response can be captured by the operator's commutator, the expectation value of operator's commutator. Say like we studied the linear response of operator O with respect to a deformation of operator A. And this quantity to the linear order, the difference between this term and this term is like this, which is expectation value of the commutator of these two operators. And in classical mechanics, we have a similar thing. Say we have a gauge invariant quantity. Oh, by the way, in the following, we will only discuss classical mechanics. So I will not distinguish quantities or operators. They mean the same thing in the following talk. So for two gauge invariant operators F and G, their bracket can be interpreted as the linear response of quantity F to the deformation of the action by minus G. And I will explain it later. To describe this formalism, we need first to review the symplectic geometry and covariant phase-space formalism. The Hamiltonian mechanics can be described by the symplectic geometry, where the phase space is an abstract manifold equipped with a closed non-degenerate 2 form, which is usually referred as the symplectic form. And this symplectic form can be written like this, where omega AB is an antisymmetric 0-2 type tensor, whose reverse is related to the Poisson bracket like this. In this formula, this omega inverse is a 2-0 type tensor, and third F and third G are one form. Contracting with the 2-0 type tensor, it gives us a scalar on the phase space. And in the following, and in this talk, I will use dirt to denote the total derivative on the phase space. And in the following, I will also use it as a total derivative of the set of configurations or set of solutions. To compare with the standard Hamiltonian mechanics, we can choose a coordinate such that the symplectic form can be written like this, and then we can write down the Poisson bracket with this formula, and you see that the Poisson bracket is precisely the one that we know in classical mechanics. In symplectic geometry, the Hamiltonian flow is an important notion, which means that given any operator which is a scalar on the phase space, it corresponds to a vector on the phase space, which is usually referred as the Hamiltonian flow. And the relation between this vector field with this vector field can be defined by this Hamiltonian equation like this. Here, the G is a test function. And if we choose this F as the real Hamiltonian, then this vector field can be regarded as the evolution on the phase space. And acting this vector field onto the test function, it gives us the time derivative of this time function. And on the other hand, I said that in the right-hand side, this omega inverse, it is the Poisson bracket. So you see that this Hamiltonian equation is precisely the old version of the Hamiltonian equation. And we can also move this omega inverse to the left-hand side, then the Hamiltonian equation can be written like this. And as a cross-check, we can compare the tensor structure. So in the left-hand side, this is after variation, it gives us a 1 form. And in the right-hand side, this omega is a 2 form. Contracting with the vector, it gives us a 1 form. So the two sets has the same tensor structure. And with the Hamiltonian flow, actually, we already know everything about this operator. And the Poisson bracket can be directly read out by acting the Hamiltonian flow of one operator onto another operator. Okay, so any question about the classical mechanics? Good. And this symplectic geometry can be realized in covariant phase space formalism, where we define the pre-phase space as the set of solutions. And the presymplectic form can be read out from the action, which is closed but may be degenerate. Note that in this case, the presymplectic form may be degenerate, which is different from the symplectic form. And the zero modes of presymplectic form corresponds to the gauge symmetries. Quotient by the zero modes, the prephase space can be reduced to the phase space, and presymplectic form can be reduced to the symplectic form. And in principle, the Hamiltonian flow and the bracket can be computed with the phase space and the symplectic form after we reduce the gauge redundancies. However, in this way, we didn't take advantage of the gauge symmetries. On the other hand, this gauge symmetry makes our formalism more complicated. We need more steps to deal with them, to cancel them. However, on the other hand, we can also keep the gauge redundancies and do computation in pre-phase space with the presymplectic form. Given two gauge invariant operators f and g, we can define the Hamiltonian flow by this Hamiltonian equation in pre-phase space, and acting this Hamiltonian flow onto onto another gauge invariant operators, we get the bracket. And indeed, that in the definition of the Hamiltonian flow, there may be ambiguities, which corresponds to the zero mode of the presymplectic form, which corresponds to the gauge symmetries. And however, because this quantity G is gauge invariant, so acting this, so even though there is ambiguities in the Hamiltonian flow, acting this Hamiltonian flow onto another operator, it is unique and well-defined. It gives us a well-defined bracket, which is the one that we define in the phase space. Any question?
Is this the Poisson bracket?
Yes, it is a Poisson bracket. It gives us a Poisson bracket. That's true. So, any question? So okay. Then from these definitions, you see that the Hamiltonian flow defined here, it is a crucial quantity from which we can directly read out the bracket. And the Peierls bracket, which we will explain in the next slides, it gives us a convenient way to compute this Hamiltonian flow in pre-phase space. And I also need to mention that in the original paper of Peierls bracket, the Peierls bracket is indeed a computation for bracket like this. However, in our setup, we just refer the Peierls bracket as a computation of Hamiltonian flow. And the bracket can be directly read out by acting the Hamiltonian flow onto other quantities in this way. And to get the Hamiltonian flow, we consider such a deformed theory with this action. Here we take a deformation for the action by quantity f.
Sorry, Jie-qiang, I want to ask a question.
Yes.
Did you have a associativity for this bracket?
Could I have a what?
Did you have associativity
Associativity.
for this bracket?
Associativity, you mean that like A multiply B multiply C, something like this? But as I know, the bracket don't have this effect. The bracket only needs to satisfy Jacobi relation. So I don't know.
What is your Jacobi identity? Could you write it?
What is, say I have, assuming Jacobi identity means that assuming I have three quantity, the bracket of f with g, like we can first take bracket between f and g, and then take the bracket between this quantity with another quantity like h, and we take a permutation for these three quantities, and the summation gives 0. This is the Jacobi identity.
Okay, okay. That is what I mean for the.
Oh, okay.
But then, how do I do a deformation?
Sorry, say that again.
Okay, for the in the non-commutative geometry, we usually can do the deformation for the Poisson bracket. So in this open string theory, we can see the Fourier product. How about here? Do you know any reference about deformation?
Do I know any reference about deformation?
Yeah.
Your question is that in some case you try to take a deformation for the theory, and you want to discuss the bracket, the effect of the bracket under the deformation. Is this your question?
Yeah, but because if you have associate like a Jacobi identity, then it's very similar to the Poisson bracket. Yeah,
it's so very similar to Poisson bracket.
At least for the edge bracket property.
I don't quite understand. So as I said, this quantity is already the Poisson bracket.
Okay, so you want to say then, but if you use this, it's okay. Okay, you want to say it's okay. If this is the Poisson bracket, then in the Poisson bracket we can do the deformation.
I don't know. I don't know how to do that. But maybe I think it is. Yeah, I think in principle you can define such problem, and I don't know
because
how to deal with
if
that.
I don't, sorry, could you go to previous page? Yeah, if I do not misunderstand, now your Peierls bracket f comma g should be equal exponential minus ihg multiply f exponential igh. Is this correct?
Sorry, I didn't follow you. You can say that.
Exponential igh multiply f, then multiply exponential minus igh, where gh is Hamiltonian. I think this is your definition for the Peierls bracket.
The definition of Peierls bracket.
So I try to understand what is your SG multiplies f. I think it's
what
like
is G multiply f. You mean what's the meaning of this quantity?
Yeah, I think it's exponential igh multiply f exponential minus igh.
Yes, you can try to interpret it in that way, but as I said that this xg, it is a vector field in the it depends on you keep the gauge redundancy or not keep the gauge redundancy, but this xg is a vector field in the preface space, and this f is a scalar function in the preface space. So that means you acting a vector field onto a scalar. This is the definition of this quantity.
I'm sorry. I think you can ask him later, and then let him move on. I think it's kind of the question session too long, so let him move on. Please go.
Okay.
Yep.
Okay.
Sorry, may I have another question?
Yes.
If you use the pre-symplectic form instead of the symplectic form, and since there's no inverse, how could you define the Poisson bracket using the definition?
Yes, this is a good question. So actually I didn't. So first, but as I said that, at least we can define a vector field in this way. And then we act this vector field onto a gauge invariant quantity. And this gives us the bracket. Because you remember that in our previous example, even though I said that by definition, the Poisson bracket should be defined by taking an inverse of this quantity. But on the other hand, I also say that I can compute the bracket in this way. Say that we first define a vector field and act this vector field onto a scalar function. So the only difference for the preface space is that there can be more than one, but at least there is one. So there is more than one choice. There is ambiguities of this vector field, but
so it depends on your definition.
Yes, but finally there is I don't want to say this is my definition. If you follow this formalism, you can show that it is. So for example, you can first caution or take a caution for all of the gauge redundancies. You can in principle you can show that this bracket is the same as the one in previous slide. Yes, but here for Peierls bracket, I want to give a convenient way to compute this Hamiltonian flow, or you can also say this is a vector field in the set of solutions, or a vector field in prephase space. And to start so any question? Okay, so let me first explain what do I mean by Peierls bracket. To start this Peierls bracket, we consider such a deformed action. So we take a deformation for the action by the quantity f, and in the following computation, we only keep the terms up to the linear order with respect to k, and we can take a linear expansion for the solution, also with respect to k, and this phi 0 is a solution of the original theory. And here we only focus on two classes of solutions: the retarded solution where this h vanish at the past infinity, or the advanced solution where this h vanish at the future infinity. But none of the
So here I'm a little bit confused. So yeah. Here f is a function, but the action is a number. So I have no idea what do you mean by the deformation here.
So first this action, it is a functional of the configuration. You agree? That means given any configuration, it read out it's
just a number. Okay.
On the other hand, this f, as I said, it is also a functional of the configuration. So it's also the same. So given any, you remember that when I try to emphasize what do I mean by operator, I said the operator, at least in classical limit, it should be interpreted as a functional of configuration. That means given any configuration, I will read out a number. Then I define. Then this is a definition for operator.
So here f is not a function in the pre-symplectic form, pre-symplectic manifold.
Yeah, sorry, here I didn't explain that. I assume that this f is a function of configuration. Or another way to say is that it is a function on the set of configuration. And the set of solutions is a subset of the set of configurations. So when you define a function, of configuration or a function on the set of configurations, then you also define a function on the prephase space. Yeah, so here I already assume that all of this quantity on prephase space could be a function of the set of configurations. Maybe in the next slides I will show a very simple example. You will see all of them. And as I said that none of the two solutions, not the retarded solution or the advanced solution, are the solution of the original theory. But their relative difference is a linear solution of the original theory. And here I want to write it in a formal way. I define a vector in the set of configurations, and this dirt over dirt phi a, it is a basis of the set of configurations. And this EA, it denotes the equation of motion of the original theory. It is a function of the set of configuration, and taking a variation, it gives us a one form in the set of configuration. And contracting with this vector, it gives us a scalar on the set of configuration. And this effect that this relative difference is a linear solution of the equation is a linear solution means this quantity vanish. And this quantitative vanish means that here, even though I define a vector in set of configurations, but it is a vector of the set of solutions. That means this is a vector in prephase space. So any question about this statement? So maybe one thing to remember is that here this quantity is a vector. It is a vector field instead of solutions, or a vector in prephase space. And in this paper, we can show that this vector in prephase space, it is indeed the Hamiltonian flow corresponding to this operator. So this is the formalism for Peierls bracket. Any question? Okay, maybe I can explain it in these diagrams. So maybe in these 4 diagrams, I can illustrate these different solutions. In this picture, it is the original solution, and assuming I have a deformation here, and this one denotes the retarded solution, and this one denotes the advanced solution, and this picture denotes their relative difference, and it is also a solution of the original theory. And on the other hand, we can also start from this retarded solution, and we can evolve from the past to future. We get the original solution, and we can evolve from the future to the past. We get the evolved solution. Oh, by the way, usually we refer this solution as the evolved solution, and this one as the original solution. And their relative difference gives us the Hamiltonian flow. And furthermore, when for most of the time when we discuss the operator, the operator that we discuss only support at one Cauchy surface. For example, the t=0 surface. And then the original solution and the evolved solution can be described by the initial values at the lower side and upper side of the Cauchy surface. And one thing I need to emphasize is that usually when we use the covariant phase space, we want to keep covariance, and that means we want to treat the phase space as a set of solutions, and we don't want to clearly clarify the location of Cauchy surface. But in the following, when we really do some computation, sometimes for convenience, we still choose the Cauchy surface. And so finally, when we discuss these examples, you can judge whether in this formalism we really simplify something, or we only use some different language. But you can judge. Let me illustrate this formalism by one example, which is a point particle with this action. And the question is to study the Hamiltonian flow of this operator. And remember that I mentioned I want to define operator as a function of configuration. And you see that this one is indeed a function of configuration, which means that given any configuration, I always read out the quantity x for t=0. And I want to study the Hamiltonian flow in 2 different ways. First, I want to start it by the Hamiltonian equation, and then I want to start it by Peierls bracket. We know that the general solution can be written like this, and the symplectic, any question? Okay, the symplectic form is like this. And by Hamiltonian equation, we can directly get the Hamiltonian flow like this. And on the other hand, we can also study the Hamiltonian flow by Peierls bracket. We consider such a deformed action. And taking a variation, we get the equation of motion. But because of this deformation term, so in the equation of motion, we also have a source term like this. And we can get the retarded solution like this. And you see that for t smaller than 0 and t bigger than 0, the behavior of the solution are different. And compare the relative difference between the solution for t smaller than 0 and the solution for t bigger than 0. We can also read out the Hamiltonian flow, and you see that we get the same result. So I think in this example, I already illustrated how to play with this formalism. So any question about this example?
Oh, I have a simple example. Sorry, simple question. It seems like for the original formalism, the equation motion or Hamiltonian flow is built in the original action, but here you need somehow make some deformation to subtract the information. Why there is such difference?
Why there? I didn't understand the question.
Oh, I was just saying, originally you just have original action as north, then you can get the Hamiltonian flow. But here you need somehow deform it to get the Hamiltonian flow. So it seems that it depends on some external like response theory, something like that.
Yes, that's true.
But like the originally you don't. It seems you can avoid this, or is it implicit at some place?
Oh, I don't know how to answer this question.
Or maybe my question is too big. Thanks.
Okay. So.
Excuse me. Can you give a bit more explicit comparison with your previous discussion? For example, where is the retarded solution? Where is the advanced solution?
This one is the retarded solution.
And then their difference and that previous formula for the Hamiltonian flow. Can you give it more explicit matching before the last page?
So maybe this is a solution for the deformed theory.
Yeah.
This is a solution for the deformed theory, and from the negative term, we can evolve the solution in the original theory. Then it gives us a configuration which is like this for all of the time. This is the original solution. And on the other hand, we can start from this one, from the positive term, and evolve backward. We also get a solution in the original theory. This is the evolved solution. So the first one is this picture, and the second one is this picture.
Right.
And the so-called the Hamiltonian flow, and you remember that in prephase space, I want in prephase space in this covariant phase space formalism, every solution of the theory of the original theory, it corresponds to one point in the phase space.
Yeah.
So actually, if you want to match this solution onto the phase space, it matches to the point x0, p0. And if you want to match this solution to the original theory, to the phase space, it matched to the x0, p0 minus k. So you see that only p0 have a change. And so that's the reason I said the Hamiltonian flow is like this. The coefficient is minus. So you see that the difference of x0 is 0. The difference on p is minus k. Then divided by k, I get a -1.
I understand this in this way, but compared to your previous formula for the the Hamiltonian flow, there is integral and there is a difference between retarded solution and advanced solution, and with another, this one, right? How do you plug the solutions into this one, this formula, and get your Hamiltonian flow in a standard way? Yeah.
Oh, I see the question.
Yeah.
Actually, wait, let me think about it. Sorry, I cannot explain it in a very simple way. The reason is that here I define this vector. Here I define this vector in the set of configurations, and the phase space is a set of solutions. So that means here I define this vector in a very large space, but actually what we really want is a vector in the subspace. So you see that why you didn't see most of the integral because I already restrict to a very small space, that is a phase space. I didn't write the vector field in the whole set of configurations.
Okay.
Does that answer your question?
Okay.
Yeah, sorry, still I didn't explain it. So even though I define this quantity in such a formal way, but actually we are only interested in the case where the configuration satisfy the background configuration satisfy the equation of motion.
Mm-hmm.
But so that means here it is only we are only interested even in previous, maybe in previous case when I do the definition I didn't explain it very well. I want to restrict to the set of configurations, and when you restrict to the set of configurations, it will be like this.
So from your deformed action,
Yeah.
because it depends on x of 0, so it's not covariant, okay, right? So somehow here you have already choose a Cauchy surface.
Yes.
Because
yes.
0, okay.
Yeah, that's true.
Mm-hmm.
But this x0 is by definition because I want to study this operator.
I see. Actually, you can choose.
And then you see it is convenient to choose a Cauchy surface.
Yes, I see.
Yeah. Since the time is not enough, so I should not give more comment. So that maybe let me still make a comment. See here actually here we have two ways to interpret these solutions. One way is that to match the solution to there when we match a solution to a point on phase space, we have two choices. One choice is to match each of the solution to each point on the phase space. Another way is that we choose a Cauchy surface, that is t equals to 0 Cauchy surface, and then we read out the initial values, that is x0 and p0, and we match these two quantity on we regard these two quantity as the parameter in phase space. But technically there is no difference. So now we already have this Peierls bracket formalism, and however maybe this example is too simple. And as I said in the very beginning, we want to study operators in gravity. So let's go to the gravity theory, and we want to consider Jackiw-Teitelboim gravity. The first example is pure Jackiw-Teitelboim gravity, and I want to study the Hamiltonian flow for the area operator. And by area operator, we mean the following thing. So in gravity, when we define a configuration, we need to clarify both the solution and also the location of the Cauchy surface. For example, we can choose a Cauchy surface like this, or we can choose a one which vibrates around this Cauchy surface, but it has the same endpoint at the boundary. And by this area operator, we mean the geodesic length between the two endpoints of the Cauchy surface. And we want to study this Hamiltonian flow of this operator. We first started by the Hamiltonian equation, and then we started by the Peierls bracket formalism. In this pure Jackiw-Teitelboim gravity, actually the phase space, the theory can be completely solved out, and the phase space only have 2 dimensions. And we choose we parameterize the phase space by 2 quantities. The first is the geodesic length between the 2 sets, and another is the relative angle between the geodesic with the spatial boundary. And in this diagram, I draw a lot of vectors. They are the tangent vector, normal vector. I want to use these vectors to define the angle between the geodesic with the spatial boundary. And the symplectic form can be solved like this. And by Hamiltonian equation, we can directly read out the Hamiltonian flow like this. And maybe one explanation for this is that when we turn on the geodesic length operator, then it will try to pull the 2 sets towards each other. And then this relative angle between the spatial boundary with the geodesic length, it will tend to decrease. So we have a minus sign here, and this is a Hamiltonian flow. But by the physical meaning of the physical explanation of this is not important. And in the following, I want to use the Peierls bracket to reproduce this result. And as I mentioned that, yes.
Sorry, Jie-qiang, what
yes.
is phi leader?
What is what?
What is phi leader?
Phi 0?
Oh, okay. If phi leader finish, what happened?
I didn't hear clearly what you said. What is? Are you asking about this phi 0?
Yeah, because if phi leader vanishes, then SH is divergent.
Oh, sorry, phi 0 cannot vanish. It is a boundary condition for the Dilaton field, and it is non-zero here.
Okay, it must be non-zero. Okay. So do you mean that phi leader should be larger than epsilon?
In this case, I take phi 0 to be a constant and take epsilon to 0. I mean, I assume this epsilon is a small number.
So I mean, you mean that the epsilon is like cutoff? So phi leader should be the epsilon.
Yes, yes.
Thank you.
Yeah, now I want to start the Peierls bracket. I want to start it by Peierls bracket. And I consider this deformed action like this. And this is the equation of motion. The first one is conjugate to the variation of Dilaton field, which is not changed. That means this configuration is still ADS2. The metric is still ADS2. And the second one is the one which conjugates to the variation of metric. And you see that it has an extra term because we take a deformation. And actually, this geodesic length, it is a function of configuration. And taking a variation with respect to the metric, this term will also change. And actually, it has two contributions. The first contribution comes from a directly variation of the metric, which behave like this. And the second one comes from the variation of this curve. But this curve is the geodesic length. And taking a variation to the linear order, it will not contribute in the length. So the variation, so dirt A only have such a term. And to solve this equation, we can take an ADM decomposition and contract these tensors with different vector, contract it with the normal vector or the tangent vector. So the first one is the normal vector, and the second one is the one for tangent normal vector, and this one is for tangent vector, to contract with tangent vector. And for this equation, I only focus on the region close to this geodesic. And from the first two equations, we can solve the Dilaton field and its time derivative. A question? Okay, so we can solve the Dilaton field and the time derivative. Actually, from this equation, we only know that the time derivative of the Dilaton field is a constant, and we can fix it at the spatial boundary. And inserting these two equations into the third one, we can read out the relative difference of the area and the relative angle with the spatial boundary. And you see that between the two sides of the geodesic, the area term is the same, but the relative angle change by this. And from this relative difference, we can read out the Hamiltonian flow. So you see this one is the same as the previous one. And so from this example, maybe you have more confidence on the Peierls bracket computation. So any question about this example? Okay. Now we are ready. Oh, yes.
I have a very simple question. If I take the area goes to take the area being little.
I don't know how to deal with that. Here I assume that this error is positive.
Yeah, but I just want to ask a consistency question. If I take A being little, then XA should be little.
If A is 0, XA should be, I think if A is 0, then XA should be divergent by definition from this equation.
But from the right hand side, SA should be little.
Yes.
So this is why I'm confused.
I don't know. I didn't think about that. I always assume that the in the configuration, the geodesic lengths between two sets are positive.
Okay.
So maybe we should talk about gravitational dressing because this is the goal of this talk. So now we finally are ready to discuss the gravitational dressing. But to have gravitational dressing, at least we need matter fields. So we consider a theory with a Jackiw-Teitelboim gravity coupled with a massless matter field, a massless scalar. And for the following discussion, we need to clarify the initial values, which include the induced metric, the extrinsic curvature, the dilaton fields and its time derivative, the matter fields and its time derivative, and the relative angle with the spatial boundary, which need to satisfy these two constraint equations. The constraint equations, they correspond to the diffeomorphism symmetries, and they are the equation motion conjugate to the variation of the metric contract with the normal vector and the normal tangent vector. And we want to consider such a gravitational dressing operator, that is the one by shooting geodesic orthogonal to the boundary with some given distance. And this geodesic should satisfy this geodesic equation. And we want to study the Hamiltonian flow of this operator. And this curve, it is a functional of the metric. And taking a variation for this geodesic equation, then we see that this third y satisfy a differential equation like this. And I think this answers the question whether this operator is a local operator or non-local operator. And you see that when you see that this third y can be written in this way. Here I take a decomposition with respect to the tangent vector and the normal vector. And this alpha s and beta s, they are some integral over the variation of a metric. And note that in this case, this third y include the terms like this, which is the variation of the metric contracted with the tangent normal vector, and also terms like this. It is these terms that make it different from the one in previous example. And to study the Peierls bracket, we following this formalism, we take a deformation in the action and we read out the equation of motion. The first one still tells us that the solution is ADS2. The second one is for the matter field, which has a source term. And the third one is the one which conjugates to the metric. And to study the equation of motion, we first extend this geodesic smoothly to the red boundary. And we want to study the relative difference of the initial values between the upper side and the lower side. First, for the matter field, you see that from this equation, we see that the matter field is continuous, but its time derivative is not, and it has an extra source term like this. As for the matter fields, you can see that the dilaton field and its time derivative do not change out of the geodesic. So it is not changed at this region. But both the dilaton field and its time derivative change on the geodesic. Let me give some comment about this solution. So first, the metric is still ADS2. And the discontinuities only appears on the geodesic. This is reasonable because this operator only supports on the geodesic. And the dilaton field is not continuous there. And this configuration satisfies the constraint equations. This means that assuming that the configuration in the lower side in the lower side of the Cauchy surface satisfy the constraint equation, then the configuration in the upper side will also satisfy the constraint equations. And the last one, maybe the most strange effect, is that this dilaton field at the spatial boundary, the change of the dilaton field at the spatial boundary is non-zero, which means that to satisfy the boundary conditions, the boundary needs to jump along the normal direction. And so even the derivation is a little complicated, but the result is quite simple. So let me give some algorithm for this Hamiltonian flow. To study the Hamiltonian flow, we first shoot geodesic and find the endpoint. And we extend this geodesic smoothly to the red boundary, and then we get a whole Cauchy surface. The metric is still ADS2. And from this source, we insert a source term here for the matter field. And from this, we can solve the matter fields from this source term. And then we can solve the dilatant fields by solving the constraint equations on the upper side of the Cauchy surface, where we need to assume that out of the geodesic, the dilatant field do not change. And the last step is to allow the boundary jump along the normal direction to satisfy the boundary conditions. So any question? Okay, good. So far we already have the Hamiltonian flow, but maybe this algorithm is too abstract. From this, it's not clear what we can really get. And so to better understand this Hamiltonian flow, we can act the Hamiltonian flow onto other gauge invariant operators, which gives the bracket. Here we take the ADM energy operator, and then the bracket between this is the left-hand side of the ADM energy. The bracket between the ADM energy operator with this gravitational dressing, it behaves like this. Here I already take on renormalization, and this minus log epsilon, it is the divergence of the geodesic length. And we found that this result is consistent with Schradien series computation. And actually, we can also define some other operator. Remember that in a free scalar theory, with on a Cauchy surface with a scalar field and its time derivative, we can construct all of the operators. So here is similar. We can also try to define an operator like this, which is a normal derivative of the scalar at the end point of the geodesic. And with proper combination of these two operators, they like take an integral and combine it with proper coefficient, we can define a creation operators which create a wave packet with a center of location and a center of momentum. And then in classical limit, the commutator between the Hamiltonian operator, between the ADM energy operator with this creation operator can be approximated by the Poisson bracket. And furthermore, can be approximated like this. In this final step, I take a shortcut. I directly use the result of this example, and I replace this time derivative of this psi by minus I cape psi. This trick is introduced in one of Gidding's paper, and I directly use that trick. And from this relation, you see that this creation operator, it is an eigenvector of the ADM energy in the adjoint representation, and this coefficient gives its eigenvalue, and so you see that the coefficient of this one gives the energy change after we create a particle. And you see that when the geodesic is small, this ADM energy increase, and when the geodesic is long, the ADM energy decrease. And assuming that the background is multi-shock wave configuration, the critical point is at the event horizon. So this is the result that I want to derive. And remember that at the very beginning, the motivation to study this gravitational dressing operator is to understand the Marolf-Polchinski firewall argument. In their argument, they use an effect that is creating a particle behind the event horizon. The ADM energy will decrease. In their original argument, they get this result more or less by the field theory in curved spacetime, and they also use some Killing some intuition from Killing symmetry. And here we try to study the commutator between this creation operator with ADM energy more careful, and we get the same result, that is creating a particle behind the event horizon. The ADM energy decrease, but it's still not very clear whether we can make some comment based on this effect, because in this derivation there are still a lot of loopholes. For example, we are not sure what is the typical state. For example, here I'm assuming this is the background is multi-shock wave configuration, but we are not sure whether the multi-shock wave configuration is a typical stage. And here we take a special gravitational dressing, but it's not clear what is the most natural gravitational dressing. So even though you see maybe this shooting geodesic is a reasonable gravitational dressing, but it's not clear. And furthermore, in this discussion, we only deal with classical limit, and we don't know how to deal with quantum correction. And as a conclusion, in this work, we developed the Peierls bracket in covariant phase-space formalism. We studied the Hamiltonian flow of gravitational dressing operator and also studied the bracket with other operators. So up to now, we only deal with simple examples. Hope this formalism will have more applications in future. And thanks for your attention.
Thank you very much. Is there any question?
All right. Is there any proof on the simple proof on the equivalence between this Peierls bracket formalism and the old Hamiltonian flow formalism?
Yes, it is in our first paper.
Oh.
It is in this paper. So actually this is not apparent. You remember that we defined the bracket in the covariant phase-space formalism, and in that formalism the bracket is well defined, even though it's hard to compute. So it's not clear that with this linear response it also gave the same result, but finally we show that they gave the same result. And one more thing is that it's still quite a surprise, because that by definition this Peierls bracket is not symmetric, but actually it is symmetric. So I don't know how to comment about this.
Okay.
Yeah, but anyway, so in this paper, in this paper, it is proved.
Sorry, when you say it is not symmetric and it is symmetric, you mean when it acts on gauge invariant objects is symmetric, or it is just?
I mean, by definition, it's not apparently that this is not a symmetric definition, but it is symmetric.
Even on non-gauge invariant or?
I don't know how to deal with non-gauge invariant operators. It's not well defined. Right, I think in some step it's not well defined.
Okay.
So the advantage of Peierls bracket is to make the computation more convenient, am I right?
Yeah, so you see that here we only need to solve a deformed equation motion, solve a deformed theory.
Okay. So I have another question about the Cauchy surface, because you initially you just shoot a geodetic to some point, then you extend this guy to another boundary. So this kind of extension, actually you can also choose any other extension, right? I mean, you just choose another kind of.
Not all of them. So actually, as I said, when I give a configuration in gravity, we need to clarify the location. We need to clarify the location of the Cauchy surface. So maybe we can have some redundancies. Maybe we can have some freedom, but the freedom cannot be arbitrary. We need to fix the boundary of the Cauchy surface. So in this case, it is similar. When I give this configuration, I also have a Cauchy surface, a given Cauchy surface, and here I choose a different Cauchy surface, but the endpoint must goes to the same. So
okay, I see.
Any other questions? Okay, if not, let's thank the speaker, whatever method.
Oh, thank you.
Oh, thank you, thank you.
Shall we leave this space open a little bit for informal discussion? I don't know. I mean, whichever, or we can just close the meeting, whichever.